Let us start again. So what did we do in the first lecture? We introduced our inner products on the spaces, and then we saw this very important statement that if you have an inner product, then we automatically have a norm. So that means now we are back in the setting of the topic of the first two lectures, namely norm vector spaces and Banach spaces. And if you put everything together, then we finally get the definition of the Hilbert spaces that I announced to you. So the way we define a Hilbert space is to say this is a vector space equipped with an inner product such that whenever we are looking at exactly this norm, then we have a Banach space. So this is the definition. So what it says is a Hilbert space is a vector space that is equipped with an inner product So let's write down the notation for the inner product. So we have an inner product, and then the space is forced to be a Banach space with respect to the associated norm. So the associated norm, that's the one that we already found here. So this is the one that is just the inner product between V and itself to the power a half. So we worked in all details with some of the examples in the first lecture. This means that we can already now write down the first examples of Hilbert spaces. So the very first example would be to say that Rn is an example of a Hilbert space, because Rn is equipped with an inner product, and Rn is also a Banach space with respect to the norm. This is what we state here. So Rn is the first example of a Hilbert space. And then you can almost guess what I take as example number 2. I take Cn. So this is again a Hilbert space. And let's just stress the fact again that the inner product is the one I spoke about in the first lecture. Namely, we have to take the sum xk, yk, complex conjugated, and then the sum from k equals 1 to n. But now remember that last week we actually took another step, because we took the step from the finite sequences to the infinite sequences. So think about it. This is exactly what we did here. So let's connect it with the infinite sequences as well. So let's use the same notation again. So let's begin by writing x like this. So take x equal to x1, x2, and then it's just an infinite sequence now. And you know, we also wrote this as xk, k going from 1 to infinity. And then I already stated for you here what we saw last week, namely that for any p larger than or equal to 1, we can introduce the space LP simply as the sequences for which xk to the power p gives something that is convergent. Now what we'll do is to look at the special case p equal to 2. And you can almost guess why we're looking at p equal to 2, because p equal to 2, this is exactly the one that gives us the norm that is similar to the inner product we have here. So if you put in xk equal to yk, then what you get here is exactly xk absolute value to the power 2. So this is the same as what you get here for p equal to 2. So this is the space we'll look at. And the statement is that exactly the space L2 of n, this is a Hilbert space and again, when you say something is a Hilbert space, you always need to say with respect to a certain inner product. So we need to explain what is the inner product. So the inner product between a sequence xk, k from 1 to infinity, and yk, k from 1 to infinity. This is something we will define exactly like what we did here, except that now we take a sum from k equals 1 to infinity. So this is a sum, k equal to 1 to infinity, xk, yk, complex conjugated. Actually, if you look at it historically, it's a little bit funny, because when you see the definition of a Hilbert space, you will think that you can just go to the library and then you can find an article by Hilbert where he is considering this space. This is actually not the case. So the name Hilbert space is something that was introduced much later. So what Hilbert did was to consider exactly the space L2 of n, and then he did some manipulations with this space. And then about 20 years later, somebody did exactly the same, but in the abstract setting that we have introduced up here in the definition. So actually, Hilbert spaces is something that is done by somebody that's called von Neumann. But what he did was just to look at Hilbert's calculations for this case, and then he generalized them to just abstract vector spaces. Now, let's look at the proof. How can we prove that we have a Hilbert space with respect to this inner product? If you look at it in the book, you'll see that there's a reference here. So it has the line number 4.5. And there's a reason that I put that number. Namely, if you want to check that this is a Hilbert space, that this is an inner product, the very first thing we have to do is to check that this actually is well defined. So the very first step is that we must show that, and now I'll just write it in abstract notation, so we must show that this inner product is well defined. So I would like, if any of you could tell me, what does it mean that this inner product is well defined? What do we have to prove now? Nikki?
That is, it is a positive, real, and a finite number.
Do we want it to be positive? It's a complex inner product, so the outcome of any inner product should just be a complex number. So we don't need it to be positive, but we need something else. So Bo, I could see you had some comment.
Some converges.
You need to show that the series converges. So in order to say that by this long and complicated symbol, we mean exactly this, in order for this to make sense, we need to show that this series is convergent. Because otherwise this does not make sense. So we must show that the sum xk, yk, complex conjugated, k from 1 to infinity, is convergent. Now you have a lot of tricks from mathematics 2 to show that a series is convergent. And one of your tricks is to look at it in absolute value and do some calculations and show that this is finite. So one trick would be to look at the sum from k equal to 1 to infinity, absolute value xk, yk, conjugated, and then calculate and then end up with something that is finite. And this is something we'll do using some inequalities. And it turns out that there's a very good inequality that you probably don't know yet, but we will use it a lot in this course. And again, this is something that you will prove yourself at one of the problem sessions. So I give you a lot of warnings of what you have to do in the problem sessions. If you look at this statement, this is something I showed you already last week, but we only need one part of the theorem last week. So last week we used what we called Minkowski's inequality. This turned out to be the triangle inequality for exactly the space LP. So we used that already. But now what we will use is what is called the Hilbert inequality. And what it says is that the absolute value of a product of two numbers can be turned into something that has just to do with the first one of them times something that has to do with the second one. So you see there are some numbers P and Q appearing here, and these P and Q are some numbers that you just pick such that 1 divided by P plus 1 divided by Q is equal to 1. Now, how can we choose these numbers P and Q? You see, if we look at this and we put P equal to 500, for example, we do not get anything interesting because we don't know anything interesting about xk to the power 500. But we know something interesting about xk to the power 2 because we know we are dealing with a space L2. That means what we know is xk to the power 2 is finite. That means if we can somehow use this inequality with p equal to 2, then we are happy because then we are back in the space we are dealing with. And the good news here is that we can take p equal to 2 and we can take q equal to 2, and then we get 1 divided by 2 plus 1 divided by 2, which is exactly equal to 1. So that means if we take this inequality and we put p and q equal to 2, so this is theorem 1, 7, 3, with p equal to q equal to 2, then the inequality tells us that what we are interested in is smaller than or equal to the sum xk to the power 2, and then we take the square root of this times exactly the same with respect to yk. And both of these numbers are finite because our sequences belong to L2. So this is a finite number, this is a finite number, and therefore the product is finite. So what this means is that if you use again the terminology we had from mathematics 2, what it tells us is that the sum xk, yk, complex conjugated, this is absolutely convergent. And what we know is that if a sequence is absolutely convergent, then it is also convergent. So that means that this series is convergent. This is something that we can prove this way. Now, after that, we need to prove all the properties of an inner product. That means we need to prove linearity in the first entrance. We need to prove that if we take the inner product of a sequence with another sequence, it gives us the same when we exchange the order. We just need to put a complex conjugation on that. But all these arguments are exactly the same as what I did for the case Cn. So you remember from the last lecture, I proved that this is an inner product in all details. And all what we did there, you will do exactly the same steps for the space L2. So the rest of the proof is exactly the same as what we already did. So you can just go back and look at your notes from the first hour, and then you'll see how to do that. And I actually think it's a very good idea if you do it, because it gives you a very good feeling for the conditions we are dealing with. But I will not do it here. So now we have our very first example of a Hilbert space. That means now Hilbert spaces are just special cases of the normal spaces. They're just special cases of the Banach spaces, and this means that all what we did during the first two lectures concerning normal spaces Banach spaces. This is something we can now do in the setting of Hilbert spaces. So if you think back again to the two first lectures, you'll remember that we spoke a lot about operators. So in the first lectures, we had operators on normed vector spaces. And what we'll do now is to look at this special case where our normed vector spaces are actually Hilbert spaces. So we will use the same name for Hilbert space all the time. So the notation from now on is that whenever I write an H written like this, then this means that we are dealing with a Hilbert space. So let's consider a linear mapping that is defined on a Hilbert space. So we will denote this by a capital phi, and it should be a mapping that goes from the space H. And now you will probably guess that I want the operator to go from H and into H again. This is actually too complicated to do at the beginning. This will be the topic of what we'll do next week. So what we'll do at the beginning is to look at a linear operator going from the Hilbert space into the complex numbers. So a linear operator going from H and into C, it turns out that they have a special name. They are called functionals. So this is not something you should worry too much about. This is just a name for special linear operators going from the Hilbert space into the complex numbers. We would like to discuss what does it mean for such an operator to be bounded. So the Hilbert space, by definition, it has an inner product. And by definition, we also look at the norm associated to the inner product. So the norm of an element V is exactly as I stated here, the inner product between V and itself to the power a half. So we have an operator going from the H and into C, and C is also a normed vector space. So the norm on C, this is just the absolute value that you know very well. So let's write down what it means that such an operator is bounded. So I think maybe it is easiest if you also look at the definition, the general definition of a bounded operator. So this is what we did last week. We considered a mapping from any normed vector spaces V1 into another normed vector space V2, and then we say that this is bounded if there exists a constant, positive constant, such that the norm of T per V is smaller than or equal to this constant K times the norm of V. So this means that the phi we are looking at, this is bounded if there is a constant K greater than or equal to 0, such that, so if you just look at this definition, then what it says is that the norm of phi for v should be smaller than or equal to k times the norm of v. But let's be careful with the spaces we are dealing with. Phi of v is something that is sitting in the complex numbers. So this means that the norm we have here, this is the norm of the complex numbers. This is the norm in the Hilbert space. So this is with an index h. So what does this mean for us? Since this is just a complex number and the norm is just the usual absolute value, what we have here, we can equally well write it just as 1 bar and then phi of v, that this should be smaller than or equal to k times the norm of v in h. So the question is, when is this condition satisfied? So let's look at a small example. So let's pick any element in our Hilbert space. Let's take any w. And then we define phi of v. So phi of v, according to what we are saying here, this should just be a complex number. And the way I'll define this complex number is to say phi of v, this should be the inner product between v and this given element, w. Then this phi is linear. And actually this is something you will do at the exercise today, but the steps you have to say is to show that this is linear means that you put in a linear combination, some alpha times v plus beta times u. That means you put in alpha v plus beta u. But then you see right away you have a linear combination in the first entrance of the inner product. And then the rules for manipulating with the inner product says that you can split this out as a sum of two inner products. And then if you look at what comes out here, then you will see that you get the linearity. So this is simply to look at one of the conditions in the definition of an inner product. Then you get the linearity. But it is also bounded. And again, if you look at one of the inequalities we have stated today, then you'll see right away that this is bounded. So I will not do it for you. I just state it as an example. So this is an exercise today. So what I'll do, instead of giving the details of this example, I'll look at a more complicated example, and I'll do that in all details. So what we'll consider now will not just be one element in the space like what we did here. Here I say, let's just fix one element in the space. What I'll do is to look at infinitely many elements in the space. So we look at a sequence vk, k equal to 1 to infinity. So I let this be a sequence of unit vectors in the space H. So that they are unit vectors. This means that they have length 1. So what this means is that vk in norm is equal to 1 for all k. So let's define the phi. So again, phi should be something that goes from the Hilbert space H into the complex numbers. So I need to find a way to tell you how can phi of v be a complex number. And the way I want to define it is to make a sum of the number 1 divided by k to the power 2 times an inner product between v and vk. And then we make a sum of this from k equal to 1 to infinity. So that means whenever you give me a vector v, what we do is to put it into the inner product and calculate the inner product between v and then these given vectors vk. And the number that comes out, we multiply it with 1 divided by k to the power 2, and then we make the sum over all k. So what I want to show is, and you will see we take exactly the same steps as we did last time. We first show that phi is actually well-defined. Then we show that phi is linear. And then finally, we show that phi is bounded. So this is what I also told you last week, that even though there are a lot of new material in Mathematics 4, then there are also some exercises that are standard exercises that come back again and again. And you will know it from last week, and you will see it again this week, that to follow this program for an operator is something that we'll do repeatedly in this course. Okay, so let's take them one by one. So we need to show that phi is well-defined. And exactly like in our previous example, to be well-defined, this means that we must show that this series is convergent. And how did we do that? So you see, this is exactly the situation we had up in this example where we worked with L2 of n. What we did was to look at the similar sum just with absolute values on the terms. So let's do the same again. So we look at the sum, and then we put in absolute values here. And we make the sum from k equal to 1 to infinity. Can any of you tell me, how can we manipulate on this to show that this is actually finite? Rune, you have an idea?
Yeah, I think that the inner product is less than or equal to 1. So you can say that.
So you want to do something with the inner product. So we make an estimate, and then you take the sum, k equal to 1 to infinity. What do you do with 1 divided by k to the power 2? You don't do anything, you keep it. And then you have the inner product, v times vk.
Yes, I can say that is less than or equal to 1.
Not exactly less than or equal to 1, but you're very close. So you say the absolute value of this, how can we estimate that? Bjørn? We need to take more steps, but this is correct. So the Schwarz inequality says that this is smaller than or equal to the norm of the first times the norm of the second. So this is the norm of v times the norm of vk. So let's just put the Schwarz back again. So you see, Schwarz, this is the one we had here in our theorem from last hour. So this is what we get at the first step. But this is equal to 1. The norm of vk is equal to 1 because this is our assumption that we are dealing with a sequence of unit norm vectors. So all of them are equal to 1. So this means what comes out here is the same as the sum, k equal to 1 to infinity, 1 divided by k to the power 2 times the norm of v. And the norm of v, this is just some number, and this is a convergent series. So therefore, we know that this is finite. So what this tells us is that, and now I write it again in all details, we know that 1 divided by k to the power 2, inner product vk. I skipped to put all these indices because you know exactly what we are dealing with. So what we have shown now is that this is absolute convergent, and therefore it is convergent. So as you see, we have to put in quite some details in order to show that the operator is well defined. The good news is, as I told you last week, that very often when you have showed in details that an operator is well defined, more or less you get the proof that it is bounded for free. And this is what we'll see again when we hit the point 3, that all the details we put in here, they actually give us point 3 without any additional work, or almost without any additional work. But before we do that, let's look at the linearity. So to show that phi is linear, we need to look at phi of alpha v plus beta w. Now we know that everything is well defined, so we can just take this and put it into our definition. That means we put it into the place of v. That means we put this linear combination in here. So we get that this is the sum k from 1 to infinity of 1 divided by k to the power 2. And then we get the inner product where we put in alpha v plus beta w, inner product with vk. And here we can make a lot of manipulations, because here we have an inner product with a linear combination in the first entrance. So the definition of the inner product tells us how we can split this. So this is the sum 1 divided by k to the power 2, and then we get alpha v inner product with vk plus beta w inner product with vk. And all of this have to be multiplied with 1 divided by k to the power 2, so we need to put a parenthesis around this. But now you can see you actually have two terms, and you have a sum of this, so you can split this into two terms. So what you get is one sum that would be sum of 1 divided by k to the power 2 times just the v inner product with vk. This has to be multiplied with an alpha, but alpha is just a constant, so we can put that out from the summation. And we can do exactly the same with the second term. So here we get 1 divided by k to the power 2, which has to be multiplied with inner product w vk. And there's a factor of beta, which is constant, so we can take it out. So we put it here. And if you look at this, you'll see this is exactly alpha times what we have here. This is phi of v. And what we have here is the beta times, and this is phi of w. So that means phi of any linear combination is the same as just alpha times phi on the first vector plus beta times phi on the second vector. So this shows the linearity. So now the question is, do we get the last point for free, or do we have to do some work? So at least what we have to show is that phi is bounded. And phi being bounded, this is something we formulated this way at the end. So we need to look at the absolute value of phi of v. So this is absolute value of, and let's put in the definition of phi of v. So this is the sum 1 divided by k to the power 2, and then inner product between v and vk. So can any of you tell how can we proceed from here? Yeah?
Yeah, we can say that it's smaller than or equal to the one way could be numerical brackets inside the sum.
So you put the absolute value inside, so this is smaller than or equal to, and then you get the absolute value inside, so this means 1 divided by k to the power 2, vk, with absolute value inside. This is correct. And then?
Yeah, then we can do the same as we did before.
Hopefully you will not do the same.
No.
Hopefully you just look at what we did.
Then we can look at what we did before, and then we can use that.
Yes, exactly. So look at what we have here. This is the sum of the absolute value 1 divided by k to the power 2 times the inner product. This is exactly what we were calculating in order to show that the operator was well defined. So if you just look at this calculation, we know that this is smaller than or equal to, and where did we end up? We ended up here. So this is smaller than or equal to the sum 1 divided by k to the power 2 times the norm of v. And this is simply by looking at the calculations. So can you also formulate the conclusion?
Yeah, so it's bounded.
So phi is bounded because this is indeed smaller than some constant, namely the constant here, times the norm of v. So that means we have shown exactly the existence of a constant to put in here. Now, we also had a special name for the smallest constant to put in here. The smallest constant was the one we denote by the norm of phi. So there could maybe be a smaller constant to put in. So what we know at the end is that the norm of phi is at least smaller than or equal to the sum. Which is a number that we know, so this is pi to the power 2 divided by 6. So nobody asked for that conclusion, but this is actually what comes out of the calculations as well. So this proves in all details that we actually have a bounded linear functional defined by this. There's something that is a little bit strange here. So I gave you an example. I gave you two examples now. So we had this example where the phi of v was just given by inner product with one given element. This is what I more or less left to yourself. And then we did this quite complicated example where we looked at something that is defined in a much more complicated way. But it turns out that all functionals can actually be written this way. So that means even this complicated expression we are looking at here, this actually has this shape if we choose this vector in a good way. So this is a very important statement, and this is what I'll show for you now. But actually, it is a quite complicated statement, and it's a very complicated proof, so we will not give the proof of that statement. But what it actually says is that all bounded functionals they actually have the form in, and did I give it a number? So maybe we should call it something. I think we did not have any example 3 yet. Is it correct? I don't remember if we had something I called example 2. But for sure we did not have any example 3, so let's call it example 3. So you see, sometimes I put a number on the example, sometimes I don't. And if I don't put a number, this is usually because I don't plan to use that example again. So the theorem says that now let's look at any bounded functional. So this means phi is any bounded linear operator going from H into C. That means it could be the one we considered in this example, but it could also be the more complicated one we are dealing with here. Then what the statement tells us is that then there exists a vector, and actually a unique vector, W in H, such that phi of V has exactly the form that we saw up here in the first example. So that it has exactly this form. Actually, I did not plan to ask you about that, but now I'll do it anyway. Can any of you see how W look like in this example? So now, if you want to refer to that, then we also need a number for that. So let's call this example 4. Bjørn?
I would say a sum of all the vk's divided by k squared.
It is 1 divided by k to the power 2, and then vk, exactly. So if you look at this vector, and you take the inner product with the v, and you do calculations, that means you move the sum outside, then you end up with exactly this expression. So this is something I will leave to you, but you can actually do these calculations, and then you'll see that this complicated functional, this is actually exactly given by this if you put in the W equal to this. So in this example, it is possible more or less to guess how this vector would look like. There are much more complicated cases where you cannot just guess how the vector would be. So the important statement here is that you can always find one vector W such that the functional takes this form, and moreover, it is unique. That means there is only one choice of your W that you can put in here. I think you had enough of the abstract mathematics for today, but before I let you go, I would actually like to connect the mathematics with physics. So, you know, Hilbert Spaces is not something that mathematicians have done just because they thought it was funny to do it, but for example, for Neumann, as I spoke about, he did it because he was interested in quantum physics, quantum mechanics, so he could see that Hilbert Spaces would be a very useful tool in the setting of quantum physics. So I would like to show 3 or 4 slides for you where I connect what we have discussed today with the physics and the quantum physics. So this is not something that I will ever ask you any questions about, but I think it is useful to know that. So before I go into the physics, I'll just tell you that today we only introduced one new Hilbert space, but what we'll do later in this course is to look at some other Hilbert spaces. Namely, we will look at the space L2 of R, which is the set of functions f going from R into C. And you can see the structure is very similar to what we had for the sequence space. Now, because it's a capital L, it's a space that has to do with an integral over R. And the number 2 means that we are looking at f of x in absolute value to the power 2 dx, and we are asking for this to be finite. So this space is something we will deal with about week 7. Now, what the physicists are doing is they are looking at the higher dimensional space, so they are looking at L2 of Rn, meaning that they are looking at functions on Rn into C, and then you have exactly the same definition, except that you are integrating over Rn instead. So this is the space we'll discuss now. So I know many of you are not familiar with quantum physics, but there's something that all of you know a little bit about, namely classical physics. So let's start with classical physics. So classical physics, this is something that deals with big particles or big objects that are moving with not too high speed. For example, you might take a slide like this, and then you put a stone here, and it runs down the slide. So this is a quite big object, and it is moving reasonably slow. So to deal with such objects, you don't think about quantum physics, you think about the classical mechanics. And classical mechanics tells you that there are a lot of rules, there are Newton's rules and so on. And if you want to know exactly where your object is to a certain time, you can calculate that, and you'll know exactly that this is true. So you can calculate the speed of the object, you can calculate where it is, and everything is something you know for sure. This is the difference to quantum mechanics, because quantum mechanics is not dealing with large objects like a stone that rolls down a slide like this. Quantum mechanics deals with small particles. And then you see there are some serious differences here. And this is what I try to tell you here. Actually, I sent you these slides also when I sent the weekly note at the end by the week. So it turns out that in quantum mechanics, it does not make sense to say that your small particle, which could be an electron or something like that, that it has a certain position and a certain momentum at the same time. The Danish word for momentum is impuls. So you cannot define the position and momentum simultaneously. And the reason is that these particles are so small that if you try to measure their speed, then you disturb them, and therefore the momentum will be changed. So just the process of measuring on these particles will change everything. So therefore you cannot define it in a reasonable way. The new thing in quantum mechanics is that we can only predict that a particle will have a certain position or momentum. You can only predict that in a probability sense. That means you can only say there's a certain probability that your object is here, or there's a certain probability that your object is here. So this is the difference to the setting of classical mechanics, where you don't speak about probability. You know exactly that after 5 seconds your stone will be here, for example. But you don't know that in quantum physics. So I'll speak a little bit about this, and I'll do it in the setting of what we call physical systems. So those of you who are physicists will have an exact definition of what a physical system is. The rest of us, including myself actually, should just think about one particle that moves in a certain potential. So there's a certain force that moves this particle around. So what is quantum mechanics? Quantum mechanics consists of a lot of postulates. That means somebody tell you there is a rule 1, there's a rule 2, there's a rule 3, and so on. I think there are 6 rules altogether. And the way they tell us that these rules are reasonable is not like in mathematics where we prove something, but what they do is they make some experiments, and then they check that the outcome of the experiments is exactly the same as what is predicted by these rules. So this is different from what I'm doing here. We also have axioms in mathematics, but I use these axioms to formulate some theorems, and then I give proofs. The physicists don't give proof, they just verify that these axioms give the right consequences. The first of these postulates, the first of these axioms says that to any physical systems we can associate a so-called wave functions that gives us all the information about the system. So what we'll consider is just a physical system that consists of just one particle that moves around. And then we will let R denote the position, we let T denote the time, and then it turns out that this wave function that contains all the information about the system, this is a function of the position and the time, and the function satisfies this condition. So the question is this something we know, this condition? Yes, this exactly means that we are in the framework of this Hilbert space. Now, usually this integral is independent of t. And this means that you can just divide this function by a certain number, and then you get that this is exactly equal to 1. And those of you who have probability theory will know that if you have an integral of something, and this integral turns out to be 1, then you can interpret this as a probability density. And what people are doing in physics is that they say, this function is a probability density, meaning that if you multiply this with a small volume element, then this measured the probability of finding the particle in this small volume element at the time t. So that means exactly this wave functions will give us the probability for whether the particle is here, here, or somewhere else. So now you want to know something about this particle. Maybe you want to know something about the position, maybe you want to know something about its energy or momentum or anything like this. And then the physicists have a postulate for that. And they say that if you want to know anything about your particle, for example, you want to know something about its position or momentum or energy, then you can find out that by looking at a certain linear operator. And it should be an operator going from this Hilbert space into this Hilbert space. You see, we are again speaking about exactly the same Hilbert space as we have here. For example, the position of the particle is something you can find out by looking at the linear operator that takes this wave function and maps it into, you see what happened here is you put a certain constant and then you differentiate 2 times with respect to the x variable, 2 times with respect to y, 2 times with respect to c, and then you add this potential, this one that comes from this force that is pulling in the particle. So you calculate all this. This is a linear operator. Actually, there's a small problem with the physicists. They're not always very exact about the mathematics. And those of you who know all the details from what we did last week will know that there's a serious problem with this operator. Any of you remember the problem with this operator? This is one of the most unbounded operators you can ever look at. So that means, in this sense, this is completely outside what we are dealing with in mathematics 4, because we deal with bounded operators all the time. But the physicists, they have a very good intuition, so they actually get through, but the truth is, they are dealing with an unbounded operator. Now, the postulate in quantum physics, the postulate number 4, is that if you want to find some possible values of any of the observables, that means you want to find out, can the observable be here, can it be here, can it have a momentum of a certain size, and so on, then all these values, they are not like you would think about in this physical system where, for example, the stone can be everywhere, but these particles, they cannot be everywhere. They can only be at certain special places, and these places are exactly given by eigenvalues for this operator A. So that means if you want to find out where your particle is, you're looking at this operator, and then you're calculating the eigenvalues, and these eigenvalues will tell you where the position can be. And of course you will say this is stupid, because an eigenvalue is a number, so how can a number tell you where a particle will be? And that's correct. So the way this should be interpreted is, if you want to find where the particle is in the x direction, then you will find a certain eigenvalue that tells you where the particle can be in the x direction. If you were speaking about the y direction, then this is again something that is one-dimensional. This is again something that is described by just one eigenvalue. So it is correct, it is just something that has to be formulated the right way. So I think you see here that you can see the connection between quantum mechanics and the Hilbert space L2 of R3. And those of you who are physicists, and I know there are about 30 of the students on Mathematics 4 who are physicists, you will see that when you start to do calculations in quantum mechanics, you are using these brackets all the time. And these brackets are exactly inner products. And you start to move operators from one side of the bracket to the other side and do a lot of calculations, which will be exactly the topic of what we'll do in Mathematics 4 next week. So I will not show you any more details, but I found a statement that I think is funny. So there's somebody who is saying that there are a lot of good things about quantum physics, and there's one bad thing also. The good thing is it agrees with all experiments. That's the first goal. And it's a beautiful and profound mathematical theory. The only thing against the theory is that it makes absolutely no sense. And I think for people like me and most of you, this is a very true statement, because it does not make sense to say that a particle can be here and then it cannot be here, but it can be here. Because, of course, it can be continuously everywhere. So this idea that it can only be in some values that are eigenvalues of a certain operator, this does not make sense for us. But the truth is that it describes wonderful what all the experiments tell. And in that sense, it's a wonderful, wonderful theory. So I hope this connects the abstract mathematics to the physics for you. Let's meet at the problem session at 3 o'clock.